Okay. Welcome back, everybody, to part 2 of Edinburgh Geological Society 2020 Fellows Evening. We shall kick off again with Daryl Sawyer, who's going to give us a talk about the Ice Age Sahara. So I'll just leave it at that and hand over to Daryl.
That looks great, Daryl.
Are you unmuted?
Daryl, you're still muted.
Yeah, got it. Right, good evening. Can you hear me now? Yeah. My name's Daryl Sawyer, and I'm going to talk about, as Tom said, an ice age in the Sahara, more particularly the Ordovician sediments in the Tassili Niger region of Algeria. I spent the last 10 years of my career working on the Inaminas gas condensate field here on the Libyan border, though we in the subsurface team actually worked out of Hassi Messaoud, which was a town about 600 kilometers away. The reservoir for the Inaminas gas condensate field is a mixture of Ordovician pre-glacial, glacial and post-glacial sediments. And we only had a few core wireline logs and 3D seismic to look at this reservoir, which was at a depth of 2 to 2.5 kilometers. So it was decided that a field trip to the south of Algeria here in the Tassili Niger area, where the rocks outcrop at surface, would be a good idea. So this is a north-south section showing Inaminas here in the north with Triassic and Jurassic at surface, with the Ordovician down here somewhere, and the area we went to study, which was the Tassili Niger with the Dider and Hiria valleys, which we'll come to later. This is a stratigraphic column of the Ordovician in the Elysee Basin, where Inaminas sits, and the Tassili Niger plateau. At the bottom, we have Precambrian metasediments and meta-igneous rocks, and they're cut by the infracambrian unconformity. And above that, we have a sequence of Cambrian fluvial rocks, and gradually as it progresses into the Ordovician, they become fully marine, and then they become shallow marine. But a lot of the shallow marine sediments aren't easily visible because of the low angle tectonic unconformity in the area. Above this, in the Hinantian, in the Ordovician, we have the glacial sediments. The Hinantian glaciation was about 1 million years long, which is quite short as these things go, apparently. And it led to the formation of a network of tunnel valleys over a large part of North Africa. These can form a very complex network. They tend to be 1 to 2 kilometers wide, 1 to 200 meters deep. And as the ice sheets recede in advance, they become filled with glacial marine sediments. They're formed by meltwater running under pressure underneath the ice sheets. And then after some isostatic rebound, there was a widespread Silurian transgression, which laid down the Silurian shales in the area. This map shows the inferred maximum ice extent in the Ordovician, well, in the Ordovician, with the study area marked here. At this time, the Saharan craton was in the northwest of Gondwana, and it was somewhere near the South Pole, so a bit colder. So here we've got an example of some of the pre-glacial sediments, in this case the Ordovician hammer quartzites, which, as you can see, are very well bedded, fractured. They're very fine-grained quartzose sandstones, very bioturbated, and they form an important reservoir in a lot of the Algerian hydrocarbon deposits, and they're shallow marine. We later moved on to the Dider Valley. Now, this is one of those tunnel valleys, and it shows a lot of glacial features, including these glacial striations. And the glacial striations tend to be on the softer valley fill sediments because they were easier to carve than the hardened bedrock. And there were also some of these larger scale carvings or striations. These, as you can see, there's a few subsurface people for scale, and these can stretch for kilometers. Their exact origin is a matter of some dispute, but they're thought to be generally related to some sort of interbed shearing in the soft sediment valley fill. There's also some other carvings in the Dider Valley. These are from about 7000 BC, the Bubelin period, and there's a whole menagerie of animals on this slab. And they show that Sahara was a lot wetter at that time and had a savanna-like fauna. This is a typical campsite. The military are tucked away here somewhere. We had a water bowser, mess tent, two-man tents, and the food truck, which the sheep travelled in. The sheep's number diminished as the trip went on. So then we move on to the Eria Valley, which is perhaps the most famous of the tunnel valleys. Here's the village and the eastern valley. The village had straw and mud huts, but they also had good mobile phone coverage. This is the main Eria tunnel valley. This is a photo montage. So you've got the eastern valley here, and the central valley and the western valley. And as you can see from the diagram below, is a complex fill. So you've got the pre-glacial sediments here at the sides. At the bottom, though it's actually off the photograph, you have a subglacial till, which is represented by a sort of a conglomerate breccia. You have these diamictites or ice-rafted debris flows, or ice-rafted debris which falls rather than flows. You have various mass flows and turbidites interleaved with these diamictites. There are also two glacial erosional surfaces marked here. There are at least two major advances with the ice sheet. Some people think there are more. It's a matter of dispute. And over the top of the valley fill and the pre-glacial sediments at either side, you have the sediments deposited during the final retreat phase of the ice sheets in the form of prograding lobes and sheets of sandstone and various distributary channels. And these tend to be harder than the surrounding rocks, so tend to stand up on the surface as sort of ribbon features, or cordons as they're known. This is the Eastern Valley again, with the Eria oasis in it, which is said to be the home of the last crocodile in Algeria, or was the home, he's now dead. And these are some of the Ordovician interhoite pre-glacial sediments, but these are the marine sediments, and you can see they're a little grayer than the hammer quartzite we saw earlier. They also provide a lot of overhangs and caves, which are ideal for protecting some more of the prehistoric artwork, of which there was quite a lot around, actually. At the end of the glaciation, there was a period of isostatic rebound and uplift and an erosive unconformity. And then these shallow marine sandbars were deposited over quite a bit of the area. And they're thought to be similar to some of the tidal sandbars you see in places today like San Francisco Bay. And they're sort of long, curvilinear features, which you can see in this satellite image, which is a place called Gara Nessaret, which is a little bit north of the Erie Valley. After the shallow sandbars, you get the full Silurian transgression, and there was a deposition of 300 meters of Silurian shales, which formed an excellent seal. And at the base of the shales, you get a very dark, organic rich, full of graptolites, radioactive shale, which is the source for a lot of the Algerian hydrocarbon deposits. It was black in core, but it weathered white at surface, which was a shock. Unfortunately, I don't have any pictures of it, but I do have a photograph of two gentlemen out for their weekly shop. Thank you. That's it.
Okay. Fantastic. Particularly like the ending there, out for their weekly shop. Do they literally just, how far would they have to go?
Miles. You think you're out in the middle of nowhere. You've just driven off-road for miles in your Land Cruisers, and there'll be these guys walking from who knows where to who knows where. We were at one outcrop, and this chap, and we thought we were, you know, we were miles from anywhere, and he turned up with this herd of goats offering to sell us milk. It's just a bit bizarre, really.
The shop comes to you.
Yeah.
Brilliant. Are there any questions concerning Cambro, Ordovician, Silurian rocks of Algeria?
Why do the shales weather white?
I don't know. Nobody told us that. But it was, yeah, it was not what we expected.
Can I ask about the biostratigraphy of the area?
You can ask, but you might not. I am a geophysicist, Tom. Yes.
I was wondering if the constraints in the area are all, like you mentioned, graptolites, whether it's all down to graptolite biostratigraphy or whether or not other fossils are used, such as microfossils, Chaetonozoa.
No, I don't think there was much in the way of fossils for dating, because we didn't have any dating done with fossils. We just, yeah, it was mainly what A followed B.
Yeah.
Yeah.
That's fair enough.
Yeah.
So when were you out there exactly? When
from 2006 to 2016.
Not all of that time, but
Well, no, we worked 3 weeks on, 3 weeks off.
Okay.
In Hassi, because
Okay.
So it was 7-day working when you were there, but yeah, stuck on a camp, which was a cross between Butlins and Colditz, I would say.
Right. No evening entertainment.
No, but we had a pool and a free bar and barbed wire.
Incredible. Brilliant. I assume that stuff can't be published. It's you know, sort of, it's not in the public domain, all that information, all the geophysics and all the stratigraphy, etc.
Well, there's quite a bit online actually about the Cambro Ordovician glaciation. If you, yes.
But the work you were doing in particular.
No, well, no.
Okay, shame. That's why you're here tonight, to tell us all about it. Brilliant.
Yes.
Okay. Does anybody else have any questions for Daryl?
No, I was just going to say, yet another example, Daryl, you know, here we are. Oops, sorry, I was on. I don't want to talk to you from like some ghostly voice. But, you know, here's another example of, you know, I really do think you guys are unsung heroes. You have such a ball of a time. I mean, you're living in camp in the middle of the desert. And I dare say, as I say, almost everybody on this call who's a geologist has that. Tell the world, we need to tell the world, we need to inspire them about, and the importance of the work that's being done. But I mean, it is really not, if you asked a kid of 5 or 6 or 10, would they say, that's what I want to do? But if you all told your stories like this, I'd sign up. So yeah, well done, you two. They're wonderful. Thank you for sharing. Really inspiring.
Hear, hear. Brilliant. Well, let's move on to one more inspiring paleontologist and geologist. That's you, Katie. And Katie's not going to be talking about fossils this evening, alas. She'll be talking instead about mortar and limestone petrography, which is part of her job at the Scottish Lime Centre Trust. So without further ado, Katie, the floor is yours.
Hey guys, so thank you very much for letting me talk today. And as Tom says, I'm not doing my usual and talking about fossils. So when I'm not looking at fossils, I'm looking at lime mortars. So I'm just going to tell you a bit today about what I started doing my job and the reason for doing petrography of lime mortars. So really, it's exactly the same as you would do with a rock. So you're wanting to find out a lot about the structure of the material, which is particularly important in materials analysis. So in lime mortars, you get different types of lime mortar. Nowadays, the most common is your naturally hydraulic limes, which we don't actually produce in the UK anymore. But historically, lime deposits were exploited on a local scale. So quite often you will come across farms that have old lime kilns there. If you look at old OS maps, you quite often see references to kilns that are no longer there. So it was just a case of what was basically available for them to use. So the most important thing, as I say, when I'm looking at a thin section of a lime mortar is looking at the composition, but also the spatial distribution of the components in there. So that is like the texture and fabric, which is exactly the same as you would do as a petrographer and applying that to rocks. So I'm going to start with an example which is of a 12th century lime render, and this was discovered in a cistern abbey located in Ireland. The structure was actually part of a basement of a shop, so they were very unaware that this actually existed up until quite recently. And when they found, obviously, with it being in a basement, there was a lot of issues with damp and things, but in particular, the lime render on the walls was going through a lot of spalling, and there was big, huge chunks coming off there. And you can see on the surface here that it's got like a layer of paint. This is actually lime wash on the surface. So basically the client got in touch because they wanted to know exactly why this was happening, but they also thought that there might actually be some modern paint that had been applied to the surface. So what we did when we got the sample in the lab, the first thing to do is do a visual assessment. After that, I normally get XRD carried out. So that's X-ray diffraction, which will tell you the mineralogy of the sample. That's very important if you want to deduce whether the lime is a hydraulic lime or if it's a non-hydraulic lime. And we got some thin sections made of this sample because the XRD, that came back to tell us that essentially it was a non-hydraulic lime, so it was made up of calcite and quartz with quite a lot of gypsum in there. Now, gypsum is quite a common sulfate that forms through sulfate attack in lime mortars, and it's something you see quite regularly in thin sections. But what we have to do is when we're looking at a lime mortar, they're prepared slightly differently to a rock because you do have material like gypsum, which is quite soluble. You can't actually polish your sample, your sections with water. So they're usually done with an oil-based material. And this is a picture of a thin section of that render, which was done perpendicular to the surface. Now, this bottom fragment at the bottom is a coal fragment, and quite often, because the lime was burned locally, you would have a layer of coal, then a layer of limestone, and a layer of coal, and when they scooped the quicklime out, everything would just get chucked in and slaked together. So you end up with these particles of coal in there. But you also get other types of material as well. But the aggregate in this is predominantly quartz based. And you can see the binder, which is the kind of sort of patchy material here. Now this is quite uniform for a lime mortar of its age. It looks quite similar in density all over. I should point out all the blue spaces are porosity. So your thin sections like a rock, you get impregnated under a vacuum with a blue dye, a blue resin, and that just allows you to look at the pore space that's in there. And there's lots of cracks that are associated with these coal fragments. And that can happen for a variety of reasons, but it's quite important to note because it does create porosity within your material. And in this image here, you can see a lime inclusion, which is highlighted by the red arrow. And one of the main things that we're interested in lime inclusions is their shape and their texture, and what that tells us about how the lime itself was made. So in this example, it's been highlighted on the left-hand side, it's got quite a distinct margin where there's not much diffusion into the surrounding binder, whereas on this side, you can see it's got quite a diffuse margin. Now, when you're looking at that, one of the things you want to do with your analysis is try and work out what the mixed proportions are. So if anybody's ever done any sort of building or built a wall or anything in your garden, you'll know that with lime or cement, you normally have 1 part of lime to however many parts sand. So that's another thing that we try and deduce from these thin sections. But this particular lime inclusion, the reason that it's got this cracking around it, that normally indicates that it's actually undergone slaking while it's actually been placed within the mortar. So when you burn your limestone, you're removing the carbon dioxide to create calcium oxide. And then you slake that by adding water, and that causes a an exothermic reaction where you get calcium hydroxide. Now in a hydraulic lime mortar, there's 2 methods where that can harden, and that's through carbonation, which is adding carbon dioxide back into your material. So you're basically taking it round in the lime cycle back to a calcium carbonate. And that's quite important because those factors influence the hardness and the sort of overall structural integrity of your material. So having a look at another lime inclusion in here, this again shows quite a lot of cracking around the edge. And there's these spaces where there's really, really blue areas of porosity, which means these are completely isolated and being filled up with that blue resin. And again, because you've got this cracking around the outside, normally you can't see it very well in this image, you get some compression around the edges with the paste or the binder. And that just tells you that it was probably late onset slaking. So this happened while that particle was in the material. But what we were most interested in this sample was we could see from the binder itself that it was just quite a normal non-hydraulic lime. So we wanted to find out what was going on with these paint layers. So we did XRD as well in the paint layers that we could isolate, and it did come back as calcium carbonate. So you're basically just looking at lime wash. And the reason that lime wash is so good and why modern paints aren't as good is that lime wash allows your material to breathe, whereas modern film forming paints, you see it on buildings quite a lot, especially externally where stonework has been painted and you end up getting big bits of paint flaking off. So it was similar that was happening here, but instead this was actually just lime wash. So we're trying to work out the lime wash itself just looks quite typical of what you would think of a historic lime wash in thin section. But if you look at the top of the image, there's lots of stuff going on up here. And down here, you can see 2 different images. The one on the left is 2 millimeters field of view, and this one's 1 millimeter on the right here. And you can see that in between the layers of lime wash are these kind of dark layers, and that's essentially just soiling. It can happen for a number of reasons, but it's normally because the surface hasn't been washed down or prepared properly. Because this had been sitting in a basement and not touched for so long, we don't really know how much work had been done. There wasn't a record because it hadn't been listed since it wasn't actually known about. But as I said, we did do XRD, and the other thing that we noticed that there's quite a lot of gypsum in your lime wash as well, which is quite unusual. So this is an image to look at the area above. So this is the interface between your lime wash here and the rest of your binder. And in this area, it's just absolutely full of calcite. So this is reprecipitation of calcite. Essentially, when you've got moisture moving through your material, you're dissolving some of that calcium carbonate, and then it gets redistributed and deposited elsewhere, normally within pore spaces. And essentially what this was doing was creating kind of an impermeable barrier between your outer surface and your internal mortar, which was causing a lot of the front surface to flake off. And you can't actually see the gypsum in this thin section. You need to do it at higher magnification. Quite often the gypsum is interspersed with the calcite and it's very, very fine. So sometimes you will only see evidence of that in the XRD, or if you're looking under an SEM at the sample. And this is another image here just to show you the structure. And it's essentially like dog-tooth calcite. So that's just the shape of the crystals. And they basically form quite tight interlocking sort of bits in between that interface. And as I say, it just means that it creates this impermeable layer where there's moisture is not easily able to transport through. And that's where you get a lot of problem with your outer surface and your paint. And this is another image to show you. The left is in plain polarized, right? Light, and the right hand side is in cross polared, and you can see how dense that is there, and there's not a lot of blue space in this region. So that again tells us this is likely one of the factors that we're experiencing these problems. But it is important to say that if you're looking at a material that has failed, there can be a whole number of reasons, and it's really important to work with you know, the people that are working on the building. So that's the contractors, the architects, anybody that's involved with the project. It's good to try and get an idea of what's going on, because there's so many different factors that can contribute to this. Just before I move on to the next one to show you actually, yeah, so this one, the conclusion essentially to the client in Ireland was that because of this reprecipitation of calcite that had formed, it's likely that was causing this impermeable layer. However, we hadn't actually been to visit this particular place in question. So without a site visit, it's very hard to tell, because you aren't actually seeing that material in situ and how it's sort of working overall in the structure. So we sent this back to them, but they were quite happy with the results, because they had thought that there was going to be a lot of work to remove modern paint from there, but thankfully there wasn't. So what they would have done is they were just going to strip it back, try and remove that lime wash, and then clean the surface and put a new layer of lime wash on top. So they're still doing that at the moment. It's quite a long project. As I say, with it being discovered in a basement of another building, there's access problems and things. So it'll be quite interesting to see how this develops and see if they're able to solve the problem, because sometimes when you get this reprecipitation, it's one of those things that's kind of a positive feedback. You can't actually really stop that from occurring. But I thought it'd be interesting to show you a sample from Scotland, which is from the northwest of Scotland, and it's a late 19th century lime plaster. And it's from a building which is listed as category B, and it's in the northwest of Scotland. So they were first sent to me because they had this really odd occurrence that this plaster had been in the ceilings for over 100 years, and all of a sudden it started slaking by what you get called pop outs, and that's where you have those inclusions of lime that I was talking about before that haven't fully slaked with water. So then if any moisture gets into your material, it's going to cause that reaction, and essentially it causes an expansion of the particle, and it'll pop out of your plaster. And this brown material that you can see in here is hair. So if you've ever looked at any plaster, it's normally reinforced with some sort of fibre. Today we use normally synthetic fibres, but historically it was normally cow or horse hair, and particularly in Scotland we used a lot of cow hair. And that can be very important as well in the overall structure of your material. So looking at some thin sections here, this is a general overview of your lime binder. Again, you've got your blue space, which is filled up with blue resin, and the fabric looks quite binder rich. All this brown material here is the binder, and this is all your aggregate particles here, which is mostly quartz and other material metamorphic rock as well. And there is some small lime inclusions in here too, and a lot of voiding. But then when you look at closer details at these lime inclusions, you start to get an idea of what's going on. So again, in this one here, it's diffused quite well into the surrounding binder. You can't see much of an interface between those two. So that means that that inclusion itself would have been acting as binder, not as aggregate, which is important when you're thinking about your mixed proportions. But there is also fine B-lite clusters, and that would normally indicate a dirty limestone. So B-lite is a clinker component. It's a calcium hydroxide silicate, and that forms through the hydraulic reaction that forms in a hydraulic lime. But because this clinker here is actually constrained to the lime inclusion, it's probably not actually having that much of a effect on the overall strength of the mortar. And this image here shows quite a dense area of the fabric, and there's two small lime inclusions in the lower left here. And this here is a bit of the limestone, which is a dolomitic bit of limestone, and this is calcine, but it's not fully slate there. But in these lime inclusions, you can see the cracking which is observed there, and this is the dolomitic particle of limestone there. And there's some hair reinforcement. You can quite often see that in thin section, which is up there in the corner. And depending on what angle you've made the thin section, it can form some quite cool structures in there. But the thing about, this is an image of the hair actually, yes. So this is a bit where you've got hair clumping, which is very bad. You want your hair to be, or your fibres to be distributed evenly throughout your material and not clumped into one place. So even though there is some binder around these particles, around this hair, it's not, there's still a lot of porosity there, and it's just that area will be significantly weakened because of that clumping of the hair. And here is another image of a lime inclusion, which has been fully slaked, but it's not actually diffused into the surrounding paste. So you can see up here, this margin is quite distinct. So this is your binder here, and this is the lime inclusion. So it's not actually diffused. So this particle is likely acting as an aggregate rather than a bit of the binder. And again, there is some B-lite clusters. So in B-lite, quite typically under when you're looking under a microscope, it forms a kind of grape-like structure, and that's normally how people would identify it. But again, it's very low concentration, so this probably isn't having much of an effect on your mortar overall. But here's another lime inclusion, and as I said before, we were having issues with the pop outs on this plaster, so that's why we concentrated in looking at these lime inclusions, trying to find out what was going on. So there is a sharp margin on this one, and it has been overburnt, which is all the really, really dark areas there. The reason this happens is because the kilns were not controlled in the way that we would control them now. There was different hotspots within the kiln, so parts of the kiln could be burning at a way higher temperature than others, and that was just to do with how ununiform they were back in the day and how they prepared those mortars. But you can see there is one small B-lite cluster down in the corner here, which it's originated from another fully slaked and dispersed inclusion. So that when that happens, that's when you're imparting strength to your mortar, when you have these silicate minerals throughout the binder. And this is another inclusion here where there's a lot of clinker grains present. Your clinker grains, as I said, are things like your B-lite, but you also get alite as well and ferrite. So there's different phases. MD who's ever looked at Portland cements will know that they're very important components in Portland cement as well, which is why sometimes you need to do quite a lot of analysis to determine the actual composition of a binder, whether it is a cement or a hydraulic lime. But the outer margin of this inclusion here, you can see is quite well defined. And in here is all your big clusters of clinker. But there is areas where it has seemed to have diffused quite well. So there's obviously something going on with the timing of this slaking where parts of your particle are reacting, but then there's other parts that are not reacting until later on when moisture is getting into the material. This is another overburnt lime inclusion. You can see that sort of really dark colour there. And you can see that because it's been overburnt and it's been in that material, it has subsequently slaked while it's been in situ, which is when you get these sort of cracks form. And you normally know by the kinds of angles that you get between the crack and the patterns that are associated with it, that has happened because of, you know, late slaking of the particle. And you can see in the sort of cracks, there is precipitation of portlandite and calcite, and portlandite is sort of the uncarbonated version of like your calcium hydroxide, so the uncarbonated lime that's in there. And here is another image showing the cluster of belite here. So this is the little white bits you can see are the alite, and the very dark stuff is your ferrite, and the rest is your belite that shows that kind of globular texture. And the evidence from these samples showed that the lime appears to have been uncontrolled when they were burning it. And where it is in the Northwest Highlands as well, we know that there is a lot of metamorphic rock there, which means that they were probably actually burning metamorphosed carbonates. So there would have been a mixture of both dolomitic and calcareous limestones being used. Now, when you burn your limestone, if you burn dolomitic limestone, it actually reaches a clinker point at a lower temperature to a calcareous lime. So if you're putting both of those in a kiln at the same time, it's going to cause problems because your dolomitic particles will become overburnt, whereas your calcareous ones are likely to be underburnt. So essentially, in this one, we know that because of the presence of belite and wollastonite, that there was at some parts of the kiln temperatures of up to 1300 degrees C, and that's the temperatures you need to actually form those clinker. So we know that parts of the kiln would have been burning to this exceptionally hot temperatures, way hotter than you would normally. You'd normally do about 1100 for a calcareous lime. And in this image here is another image of the lime inclusion, where it's acting as part of the binder and not the aggregate. And from the sections, we think it was prepared as a quicklime initially, which is basically where you add your water to your calcium oxides, but it seems that it has been sort of left for a while before they've actually put it into the material. So what they would normally do, there's various ways that they can do this. Quite often it's, if you've got a dolomitic material, they might not have known that it was dolomite, but they would know that it behaved differently to their typical mortars. So we do have historical evidence of people taking these precautions when they're using dolomitic lime, but in this instance, it just seems like they were unaware of what they were actually using as a material. And although, so in plasters, normally you have a finishing coat on your plaster, which is gauged with gypsum. And quite often it can just be a pure gypsum finishing coat. But on this one, we could see evidence of quicklime within the finishing coat, which is very, very rare. It's just not exactly the nicest material to get that sort of flat finish that you want with your gypsum. This image here, again, shows another lime inclusion. And as I said, if these have been mixed as a hot mix mortar, it doesn't look like they've actually been used in that way. So they weren't used straight away when they were hot. So it was most likely it was slaked and allowed to cool and then remixed prior to its application. And like I mentioned, they might have known that that was because of the unsoundness of dolomitic lime plasters. But again, if they weren't, it was maybe just because stuff was burnt as it was available and then kept until it was needed, which was often the case in a lot of different sites. But it's not just old materials. So I just wanted to point out that although we do look at historic mortars, we do also look at modern materials and why they've failed. And the reason petrography is so good for this as well is exactly the same application as you would for a historic mortar, you know, trying to find out what is going on with the structure in there. So that previous sample, is there more work that can be done? There definitely is. Within science, there's always further research, but part of the argument is how far do you go in conservation? So for example, that plaster sample from the northwest of Scotland, we could have gone further and collected material from the area and burnt that in a kiln and made our own mortar and then analysed that. But the people who were actually doing the repairs, they were not going to be using a plaster like that. There's not really anybody trained in doing hot mix mortars in that way anymore. So it's very unlikely in that situation that you're going to want to replace it like for like. So that's another thing to think about when you're doing analysis, you know, to think about how far you would need to go. In this particular sample though, it's just quite interesting. This was only applied in 2019, so this is last year, and pretty much straight away it started to experience issues. And these sort of perfectly circular voids in here show that the render has been over area trained, and it suggests that it was likely because the material was significantly over mixed. So they basically mixed it too much and there's too much air in your mortar, or it's been oversaturated with mortar. And yeah, so this slide was just, I've already kind of spoken about this, about, you know, is there a need for further work? So this image on the right hand side is just an image of a Portland cement. So you can see, in contrast to the images of a lime mortar, there's very little blue that can be seen here. The only blue you really get is within cracks in your mortar, because the way Portland cement has a very, very dense texture, which is one of the arguments obviously for using lime and talking about breathability, is that it's very important to have breathability, and you want to basically suck the water out of your masonry into your lime mortar, because it's a lot cheaper to replace and repoint a building than it is to replace the masonry there. So yeah, that's just a quick brief introduction of that. So has MD got any questions?
Thank you very much, Katie. As she says, any questions?
Yeah, I'm Peter Delstrother. I've got a question. What's the source of the sulphur in forming this gypsum within the plaster? I appreciate it's in coal, but you implied there was quite a lot of it, quite a lot of gypsum.
So there's a few ways. Normally it's a reaction with seawater. So if you're looking at a building that's quite close to the coast, you do get quite a lot forming there, or de-icing salts is a big one as well. So there's various different places it can come from. It can also come from your masonry. I've seen quite a lot of examples of where the building is built with a limestone, and obviously you're getting that further reaction between chemicals in your limestone and your lime mortar, where you get gypsum precipitation. But if you're looking at Portland cement, there's gypsum in Portland cement, which forms the tight sort of needle-like structure, which is one of the things that gives Portland cement its sort of dense texture.
Yeah, I'm a cement person, so that's a different story from lime.
Yeah, it's one, like, we quite often get sent cement samples, because people, you know, if you're not aware of what you're looking at, they'll just take a sample for the most accessible bit of the building, which normally, if it has been repaired at some point, it's been repointed in cement. So it's important that, you know, if you're taking a sample, to know what you actually want to analyse and what you want it to tell you as well.
Although I'm a cement person, it's a crime to repair lime mortar with cement mortar. But gypsum and cement is used to slow the setting time, slow the setting reactions.
Okay. Yeah, and normally in lime mortars, the only time you want gypsum is in your finishing coat of a plaster. You normally wouldn't want gypsum to be forming in there at all.
I was quite surprised to you finding A-light, because 1300 C is pretty hot for an old-fashioned backyard type lime kiln.
Definitely, and we even got extra thin sections made and did extra XRD, because I was still not convinced. You know, like, looking at it, I was like, it looks like A-light, but you have to be sure, because again, sampling, like, if you look at the amount of mortar that's in a building, if you're only sampling one little bit, you know, and there's a sampling bias as well. So it's important as well to look at it in the context of the building.
Yeah, because A-light's very reactive, so you would have thought with water it would soon cease to be A-light.
Yeah.
So it's quite a very big surprise, that.
Yeah.
Big surprise.
So I have a question as well. Oh my goodness, Katie, sort of a total encyclopedic view again, you know. Geology, chemistry, the whole thing, fantastic. But I never thought I would meet anybody who was so expert. But could you explain to me, you know, the Roman, the substance that they make with using lime, and they mixed it in, and it survives underwater. It can take pressure. I can't find the name of it, but do you know what I'm talking about?
Yeah. So Roman cement. It's a lime, but it's got different properties. So there's a thing called the pozzolan, which quite often was added. So the Romans quite liked adding ceramics to their material. So in modern times, more recent times, people add like brick dust and things, usually whatever's available, but you're looking for silicates and clay minerals that when you burn them with your calcium carbonate, they create that clinker. And the clinker is the main component that imparts the hardness to your material. So,
but it's the substance that it says actually when it's underwater. So they used it for like under bridges, and I just you know, I used to think, how the hell did you figure this out? You know, so it becomes more stable, more robust. You know, when it's actually when it's wet, when it's underwater, in fact.
Yeah, so that's a hydraulic lime is a lime that will set underwater, so it can draw carbon dioxide while it's under the water to carbonate. And when we were producing lime in Scotland, like in lime kilns in Charlestown and Fife, or over in the west, and we were producing a hydraulic lime because there's a lot of impurities in our limestone here. And that's why it was quite famously used for a lot of bridges, like Dundee Harbour used lime mortar from Charlestown because it set underwater and it was so hydraulic. But a lot of that, there's still an argument as well about how much of that was impurities from your limestone and how much of it was impurities within your kiln itself, because you're going to get a lot of material sticking to the side of the kiln and getting mixed in. So it's a really like interesting sort of branch of research that there's still a lot of work needing to be done on it.
Oh, good.
Can I add a few words? I mean, or just to support what Katie's saying, the quicklime, calcium oxide, goes hard by reaction with atmospheric CO2 to go back to calcium carbonate. These things, A-lite and B-lite, cement, hydraulic lime, they are calcium silicates, and they react with water. They hydrate with water. They don't need any CO2. They go hard by hydration with water. So that's why they set underwater, and you could leave concrete underwater forever. It doesn't come to any harm at all and probably benefits it. So that's the two critical things. One requires CO2 from the atmosphere. So lime mortar would never set underwater and never be any good for foundations. But hydraulic lime, which as Katie says, can arise in a number of ways. The chemical reaction is with water. That's what makes it go hard. That's why the Romans were quite clever. Their whole empire depended on making harbours, and they discovered how to do it.
And yeah, and it's amazing some of the things that you find in material. I mean, I don't particularly look at a lot of Roman cement based material. It is normally lime based. But I do know people who study that, and some of the kind of ceramics and things that have been used to create that hydraulic component. It's fascinating that they did manage to figure that out. And a lot of people think it was just a case of, oh, we'll try this, see what happens. I mean, there is historical evidence that like Scottish mortars, there's places where like blood has been added, animal blood, to mortars and things. So a lot of that was to make it more pliable, maybe more easier to work. But again, it would all depend on like the specific worker who was doing it, because everybody would have had kind of their own techniques and things as well.
The real problem with modern cement is you have to get to the temperatures you've described, over 1300 Celsius, to get quartz or silica, shall we say, to react with calcium to make calcium silicates. But things like the ash out of Vesuvius, some of it has microcrystalline free silica. And that was sufficiently reactive at temperatures where you add lime to water, so near boiling water temperatures, to form calcium silicates. And they were the things that hydrated and went hard. So not all volcanic ash will do, but some volcanic ash, and I learned this from a woman who knew about the medical implications of ash from certain volcanoes and silicosis, that it relates to the extremely fine particle size of the silica, which allows it to react with lime at normal temperatures.
That's really, really interesting, because it's one of the reasons that we never specify a mortar in adding an ash pozzolan, because there's literally been no research done on, like, because it's so variable that you wouldn't be able to tell what it was going to do to your mortar without doing a lot of tests first and making test panels. So you could end up using it and either end up like being super, super hard or just falling apart. In Northumberland, it's quite common to get black ash mortars there. And that's where it's just because that's what's been available at the time. But it's really interesting.
Yeah, that certainly works, and people still use ash from coal-fired power stations. If you get it quickly before the silica has crystallized, it will react and substitute for cement to make calcium silicates. And so will, if you can imagine the process in a blast furnace, you're typically removing silica by adding calcium oxide and making calcium silicates. And if you do the right things with the slag and keep it in a glassy state, then you can, that is hydraulic as well. So if you mix it with cement, and the pH is so high when it starts to hydrate that it makes it hydraulic. And you can, for instance, if you're making a dam, you could replace 70% of your cement with ground slag, and it slows the heat of reaction down, which reduces it, which means you don't have water pipes all through the concrete to cool it down. So it's not so much available in the UK now because we don't have many steelworks left. But it's another example of available silicates, calcium silicates.
So is this whenever we're talking about, the environment and heat and whatever, and cement seems to be just it's up there as one of the sort of, very, very difficult stories to tell in the modern age. So does this science not scale? Is that what you're saying? There's not enough of the material to be able to replace current cement methods?
Well, we could use more blast furnace slag if it was available, but think how it got there. It's calcium carbonate being calcined to give off the CO2, and then the calcium oxide reacting with the silica in the iron ore. Mm-hmm. So you've not saved anything, except in the sense that if you were throwing your slag to waste, you would have got some benefit. But it once it's been sitting outside in the wet for tens of years, as much of it has, it's just aggregate.
So I'm sorry to sort of hog another, because there's something else flashed into my mind. You mentioned the medical. We're talking about bentonite here. We're talking about, is that not what we're talking about? So that's that's used for medical purpose. That's volcanic ash that's been used. No,
that's a clay, isn't it? The talk I went to, it was a woman who was talking about people suffering from lung problems who lived near a source, near a volcano with ash, and they found that people on one side of the valley suffered horrendously more than the other, just because of the way the finer ash with the high microsilica in. Mm-hmm. They were more exposed to it than the other. It was an absolutely brilliant talk. Fantastic.
And zeolite, is that a clay as well?
Those are minerals which form typically in vesicles in lavas. I wouldn't call them that. Somebody would not be able to describe them better than I can.
You could, no, because they are being used for example, in the medical, some of these, and again, this is the beauty of geology, guys, they are being used. If you've had chemotherapy, they latch on to these sort of, the stuff you don't want to keep in the body and take them out. And they're being used in Germany in particular. They're being used to help people recover very, very quickly from chemotherapy treatments by taking zeolite or bentonite in medical grade. Anyway, enough from me. Thank you for all of that. Really passionate. Fantastic. Wow.
Thank you, Katie, and thanks for the fascinating insight from cement specialists. And it's a perfect combination there, cement specialist with a lime specialist there. That was very fortuitous.
I spent about 4 years of my early career making quicklime, so I'm touched with both.
Brilliant. Right, we can continue these discussions for a while if you would like, but it's probably worthwhile formally wrapping up our Fellows Night for the evening. So I would like to obviously thank all of our presenters this evening. We've had a very diverse range of presentations, which I think highlights the expertise within the society and the society's friends. And that's one extremely valuable thing that Edinburgh Geological Society has, and it makes it a very strong society where everyone can learn from everybody else. Roger's talk at the beginning introduced some sort of geoconservation and sort of, I suppose, maybe slightly political sort of a political theme to trying to encourage institutions and governments and countries to appreciate and actually conserve our geological heritage, not ours alone, but the whole world's geological heritage. And then we had Rachel give a fascinating talk on sort of what actually goes on in the industry as a mining geologist. And I know that what Rachel does is just one part of mining geology, but it was fascinating to actually see the sort of out there hands-on side of mining geology. Like I was saying, when I was in the oil industry, I spent all my time in front of computers. So she's actually shown that the good side of things, I would say. And Jason, thank you very much for your fascinating and beautiful, beautiful photographs. And it's a shame you couldn't have the nice sort of mood music behind there, but I really do like the idea of putting a sort of quiz or a calendar together or something like that. So if anybody else is enthusiastic for that, then do let any of us know, and maybe we'll discuss it at the next council meeting.
I was thinking about an outreach activity, actually, that you reach out to and get, not just expert geologists, one where you actually engage kids or their families. They go for an excursion, so that you through the,
I'm making a note of this now.
I know you are. Get families out taking, the best, quirkiest photograph they possibly can of a geological phenomena. And
I think we're a bit late for a calendar for next year.
No, plenty of time for next year.
Maybe I'll hand that one over to you then, Angela. So yes, Daryl, after Jason's photographs, gave us another nice piece of field geology, looking at the Camera Ordovician glaciations in Algeria. And I'm particularly interested in that because you see evidence of certainly the Ordovician glaciation in the UK over in Wales. So there's nice parallels there. And also here in Scotland at Dobslin. And then finally, as we've just been discussing, lime mortar. And I thought that was a fantastic talk because not only was it very insightful and really quite technical, but Katie managed to convey the technicalities in the way that, well, I certainly understood. So it must have been good if I could understand it. And but I thought she also brought about sort of historical, the science and historical side of lime mortar. Around here in Midlothian, you can drive around and find old lime kilns, and Katie's talk just linked the two up for me. So I thought that was very good, and I appreciate that. So the next time somebody drives past a lime kiln, spare a thought for what Katie does. So once again, thank you everyone to all your for all your presentations. And before I wish everybody a very good Christmas, I'd just like to say that the next lecture in the new year is on the 6th of January. It's by Lucy Mackay from Strathclyde University, who will be talking about, it says here, core surprise. What's in plate tectonic boundaries, or a plate tectonic boundary? So a fascinating and interesting, curiously titled talk that I'm looking forward to in the new year. With that, happy Christmas to everybody. Have a really good break, and I look forward to seeing everybody in the new year, and season's greetings.